Going to look at something quite important, demoivres theorem. It actually is something we've seen already, but it's more formalised. So if you get a complex number and we raise it to the power of n, then we know that we multiply the argument by n. That's what it's basically saying. So cos theta plus I sin theta to the power of n would be cos n theta plus I sin theta. Now, demoivres theorem originally, I guess, said for all integers. We have since worked out that, hey, it's not only for integers, it works for negative numbers as well, it works for positive numbers, it works for fractions. And in fact, that only has a modulus of 1. It works when the modulus is anything as well, because we know with the modulus we just raise the modulus to the power of n. Now, why is this useful? Well, you get a question like 1 minus I to the power of 5. Well, alright, yes, we could expand the whole thing out if we wanted to. But what we can do is we can change it to mod arg form. The modulus is the square root of 2. The argument is minus pi on 4. So it'll be root 2 cis minus pi on 4 to the power of 5. Well, the modulus will raise to the power of 5. The argument will multiply by 5. And we get 4 root 2 cis 3 pi on 4. If we actually wanted to work out the complex number in a plus ib, the Cartesian form, well, we could then go, alright, let's expand it back out. Cos of 3 pi on 4, 3 pi on 4, that's second quadrant, isn't it? So cos would be negative, sine would be positive, and we get our answer minus 4 plus 4i. So it gives us another way of working that out, rather than going, hey, what's 1 minus I times 1 minus I times 1 minus I times 1 and so on. It also means, because we now know it works for fractional powers as well, it gives us another way of finding roots. So if z to the power of n is equal to x plus iy, what we can do is we can change the x plus iy into mod arg form, r cis theta, and then z will become the nth root of the modulus, and then the theta we divide by n. But when we're dealing with roots, for instance, square root, we want 2 solutions. And so we add in this 2 pi k. Basically we're saying, hey, yes, we know the answer is theta divided by, but we could be going around the circle. And however many solutions we want, that's how many times we'll go around. So I could say 2 pi k, sub in 0, 1, 2, 3, 4, and generate as many solutions as I need. So if I want to find the square root of 4i, we have the techniques we saw before. Or now I could say, well, 4i, I know that's 4 cis pi on 2. So z will be 2 cis, 2 pi k plus pi on 2 on 2. I need 2 solutions, so I'll sub in k equals 0 and k equals 1. And if I sub that in, I get 2 cis pi on 4 and 2 cis 5 pi on 4. And converting that back, we get 2 outside of 1 on root 2 plus 1 on root 2i, and 2 outside of minus 1 on root 2 minus 1 root 2 on I, which tidies up to be just root 2 plus root 2i and minus root 2 minus root 2i. So it's another way of finding square roots, I suppose. Because we don't have to just stop at square roots now. If I want to cube roots, I could make the power a third, and so on and so on. Another way of doing it is thinking about the Argand diagram. Okay. So there's 2 cis pi on 4. There's the first solution. The solutions are symmetric. So if 2 cis pi on 4 is one solution, it's a square root, I need 2 solutions. So the other solution must be directly opposite. 2 cis minus 3 pi on 4. They're always going to be evenly placed. So when it comes to square roots, I always know there'll be 180 degrees or pi radians between the 2 solutions. So if I want the 4th root of 16, 4th root of 16, well, 16 is 16 cis 0. The 4th root of 16 is 2. It'll be 2 pi k plus 0, so that's just 2 pi k over 4. I want 4 solutions, so 0, 1, 2, 3. So 2 cis naught, 2 cis pi and 2, 2 cis pi, 2 cis 3 pi on 2, they're actually quite easy to convert back, of course, because everything there is either real or imaginary. Cis 0 is, of course, 1, cis pi on 2 is I, cis pi is -1, and 3 pi on 2 would be down at negative I. But again, if we did it just looking at the Argand diagram, the first solution was 2 cis 0. And again, I know they're evenly spaced, so there's got to be a solution every 90 degrees. So the next one would be there at pi and 2, then pi, and then down there at, well, I've called it minus pi and 2 down there, but that of course is the same as 3 pi on 2. That'll do us for now. There's a little introduction into demoivres theorem.